Hi, welcome back to Easy Math by Dr. Nasir, your path to math confidence. Don't forget to share, like, and subscribe so you never miss a conceptual concrete lesson. Well, in today's lecture, we will see some initial value problems. We'll see an exercise. Find solution of the initial value problem dy by dx plus y is equal to f of x, where x belongs to 0 to plus infinity closed interval and y at 0 is equal to 1, where f of x is equal to 1 for x belongs to 0 to 1 closed interval and f of x is equal to minus 1 for x belongs to 1 to plus infinity open interval. Also state the interval I is subset of R over which the solution is defined and draw the graph of the solution. Well, see solution. Comparing the ODE 1.1 with standard form, we have p of x is equal to 1 for x belongs to 0 to plus infinity closed interval. So integrating factor is mu x is equal to exponential of integral of p of s dx, which is equal to exponential of integral 1 dx, which is equal to exponential x, where x belongs to 0 to plus infinity closed interval. Multiplying the ODE 1.1 by the integrating factor, we have exponential x into dy by dx plus exponential x into y is equal to exponential x into f of x, where x belongs to 0 to plus infinity closed interval. Well, this can be expressed as d by dx of exponential x into y is equal to exponential x into f of x, where x belongs to 0 to plus infinity closed interval. So we had d of exponential x into y is equal to exponential x into f of x dx, where x belongs to 0 to plus infinity closed interval. Now integrating from 0 to x, we have integral from 0 to x of d of exponential t into y is equal to integral from 0 to x of exponential t f of t dt, where x belongs to 0 to plus infinity closed interval. So we have exponential t y from 0 to x is equal to integral from 0 to x of exponential t f of t dt, where x belongs to 0 to plus infinity closed interval. So exponential x into y of x minus exponential 0 into y of 0 is equal to integral from 0 to x exponential t f of t dt, where x belongs to 0 to plus infinity closed interval. So exponential x into y of x minus 1 is equal to integral from 0 to x of exponential t f of t dt, where x belongs to 0 to plus infinity closed interval. Now for x belongs to 0 to 1 closed interval, from equation 1.2 we have exponential x into y of x minus 1 is equal to integral from 0 to x of exponential t dt, where x belongs to 0 to 1 closed interval. So exponential x into y of x minus 1 is equal to exponential t from 0 to x, where x belongs to 0 to 1 closed interval. So exponential x into y of x minus 1 is equal to exponential x minus exponential 0, where x belongs to 0 to 1 closed interval. So exponential x into y of x minus 1 is equal to exponential x minus 1, where x belongs to 0 to 1 closed interval. So exponential x into y of x is equal to exponential x, where x belongs to 0 to 1 closed interval. So y of x is equal to 1 for x belongs to 0 to 1 closed interval. Also for x belongs to 1 to plus infinity open interval, from equation 1.2 we have exponential x into y of x minus 1 is equal to integral from 0 to x of exponential t f of t dt, where x belongs to 1 to plus infinity open interval. So exponential x into y of x minus 1 is equal to integral from 0 to 1 of exponential t dt plus integral from 1 to x of exponential t into minus 1 dt, where x belongs to 1 to plus infinity open interval. So exponential x into y of x minus 1 is equal to exponential t from 0 to 1 minus exponential t from 1 to x, where x belongs to 1 to plus infinity open interval. So exponential x into y of x minus 1 is equal to e minus 1 minus exponential x plus c, where x belongs to 1 to plus infinity open interval. So exponential x into y of x is equal to 2e minus exponential of x, where x belongs to 1 to plus infinity open interval. So y of x is equal to 2 exponential of 1 minus x minus 1, where x belongs to 1 to plus infinity open interval. Thus from equations 1.3 and 1.4 we have y of x is equal to 1 for x belongs to 0 to 1 closed interval, and y of x is equal to 2 exponential of 1 minus x minus 1 for x belongs to 1 to plus infinity open interval. Which is required solution of the initial value problem 1.1 and is defined over 0 to plus infinity closed interval. Well, this is graph to the solution of the initial value problem. The graph is continuous from 0 to plus infinity closed interval. Also, graph is differentiable from 0 to plus infinity closed interval except at s is equal to 1. Well, see another exercise. Find solution of the initial value problem dy by dx plus 2x5 is equal to f of x where x belongs to 0 to plus 1 closed interval and y at 0 is equal to 2 where f of x is equal to f for x belongs to 0 to 1 close open interval and f of x is equal to 0 for x belongs to 1 to plus 20 close interval. Also set the interval I subset of R over which the solution is defined and draw the graph of the solution. Well, see solution. Comparing the ODE 1.5 with standard form, we have Qx is equal to 2x, where x belongs to 0 to plus 20 closed interval. So integrating factor is mu x is equal to exponential of integral Px dx, which is equal to exponential of integral of 2x dx, which is equal to exponential s square, where x belongs to 0 to plus 20 closed interval. Multiplying the ODE 1.5 by the integrating factor, we have exponential s square dy by dx plus 2x exponential s square y is equal to exponential s square f of x where x belongs to 0 to plus 20 closed interval. Well, this can be expressed as dy by dx of exponential s square into y is equal to exponential s square into f of x where x belongs to 0 to plus 20 closed interval. So we have d of exponential s square into y is equal to exponential s square f of x dx where x belongs to 0 to plus 20 closed interval. Now integrating from 0 to x, we have integral from 0 to x d of exponential t square into y is equal to integral from 0 to x of exponential t square f of t dt, where x belongs to 0 to plus 20 closed interval. So exponential t square into y from 0 to x is equal to integral from 0 to x of exponential t square f of t dt, where x belongs to 0 to plus 20 closed interval. So exponential s square into yx minus exponential of 0 square into y of 0 is equal to integral from 0 to x exponential t square f of t dt, where x belongs to 0 to plus 20 closed interval. So exponential s square into y of x minus 2 is equal to integral from 0 to x of exponential t square f of t dt, where x belongs to 0 to plus 20 closed interval. Now for x belongs to 0 to 1 closed open interval from equation 1.6, we have exponential s square yx minus 2 is equal to integral from 0 to x of exponential t squared into t dt, where x belongs to 0 to 1 close open interval. So exponential s square into yx minus 2 is equal to 1 by 2 integral from 0 to x of exponential t squared into 2t dt, where x belongs to 0 to 1 close open interval. So exponential s square into yx minus 2 is equal to 1 by 2 exponential t squared from 0 to x, where x belongs to 0 to 1 close open interval. So exponential s square into yx minus 2 is equal to 1 by 2 exponential s square minus 1 by 2, where x belongs to 0 to 1 close open interval. So exponential s square into yx is equal to 1 by 2 exponential s square plus 3 by 2, where x belongs to 0 to 1 close open interval. So yx is equal to 1 by 2 plus 3 by 2 into exponential of minus s square, where x belongs to 0 to 1 close open interval. Also for x belongs to 1 to plus 20 close interval from equation 1.6, we have exponential s square into yx minus 2 is equal to integral from 0 to x of exponential t square f of t dt, where x belongs to 1 to plus 20 close interval. So exponential s square into yx minus 2 is equal to integral from 0 to 1 of exponential t square into t dt plus integral from 1 to x exponential t square into 0 dt, where x belongs to 1 to plus 20 close interval. So exponential s square into yx minus 2 is equal to 1 by 2 integral from 0 to 1 of exponential t square into 2t dt plus 0, where x belongs to 1 to plus 20 close interval. So exponential s square into yx minus 2 is equal to 1 by 2 exponential t square from 0 to 1, where x belongs to 1 to plus 20 close interval. So exponential s square into yx minus 2 is equal to 1 by 2 into e minus 1, where x belongs to 1 to plus 20 close interval. So exponential s square into yx is equal to e plus 3 over 2, where x belongs to 1 to plus 20 close interval. So y of x is equal to e plus 3 over 2 into exponential minus s square, where x belongs to 1 to plus 20 close interval. Now from equations 1.7 and 1.8, we have y of x is equal to 1 by 2 into 1 plus 3 exponential minus s square, where x belongs to 0 to 1 close open interval. And y of x is equal to 1 by 2 into e plus 3 into exponential of minus s square, where x belongs to 1 to plus 20 closed interval, which is required solution of the initial value problem 1.5 and is defined over 0 to plus 20 closed interval. Well, this is graph of the solution of the initial value problem. The graph is continuous from 0 to plus 20 closed interval. Also, solution is differentiable on 0 to plus infinity closed interval except at x is equal to 1. Well, see another exercise. Find solution of the initial value problem. 1 plus s squared divided by dx plus 2xy is equal to f of x with epsilon to 0 to plus infinity closed interval and y at 0 is equal to 0, where f of x is equal to x for epsilon to 0 to 1 close open interval and f of x is equal to minus x for epsilon to 1 to plus infinity close interval. Also state the interval I is subset of R over which the solution is defined and draw the graph of the solution. Well, see solution. A given ODE 1.9 can be expressed as dy by dx plus 2x over 1 plus s square into y is equal to f of x over 1 plus s square with epsilon to 0 to plus infinity close interval. Comparing the ODE 1.10 with standard form, we have p of x is equal to 2x over s square plus 1 where epsilon to 0 to plus infinity close interval. So integrating factor is mu x is equal to exponential of integral of ps dx which is equal to exponential of integral of 2x over sk plus 1 dx which is equal to exponential of log of sk plus 1 which is equal to sk plus 1 where epsilon to 0 to plus infinity close interval. Multiplying the OD 1/10 by the integrating factor, we have sk plus 1 into dy by dx plus 2xy is equal to f of x where epsilon to 0 to plus infinity close interval. Well, this can be expressed as d by dx of sk plus 1 into y is equal to f of x where epsilon to 0 to plus 20 closed interval. So d of sk plus 1 into y is equal to f of x dx where epsilon to 0 to plus 20 closed interval. Now integrating from 0 to s, we have integral from 0 to s t of t square plus 1 into y is equal to integral from 0 to s of f of t dt where epsilon to 0 to plus 20 closed interval. So t square plus 1 into y from 0 to x is equal to integral from 0 to x f of t dt where epsilon to 0 to plus 20 closed interval. So we have sk plus 1 into y of x minus 0 square plus 1 into y of 0 is equal to integral from 0 to x f of t dt where epsilon to 0 to plus 20 closed interval. So sk plus 1 into y of x is equal to integral from 0 to x f of t dt where epsilon to 0 to plus 20 closed interval. Now for epsilon to 0 to 1 close open interval from equation 1.11 we have sk plus 1 into y of x is equal to integral from 0 to x f of t dt where epsilon to 0 to 1 close open interval. So sk plus 1 into y of x is equal to integral from 0 to x t dt where epsilon to 0 to 1 close open interval. So sk plus 1 into y of x is equal to t square by 2 from 0 to x where epsilon to 0 to 1 close open interval. So sk plus 1 into y of x is equal to sk by 2 where epsilon to 0 to 1 close open interval. So y of x is equal to sk over 2 into sk plus 1 where epsilon to 0 to 1 close open interval. Also for epsilon to 1 to plus infinity closed interval from equation 1.11 we have sk plus 1 into y of x is equal to integral from 0 to x f of t dt where epsilon to 1 to plus infinity closed interval. Well, this can be expressed as sk plus 1 into y of x is equal to integral from 0 to 1 f of t dt plus integral from 1 to x f of t dt where epsilon to 1 to plus infinity closed interval. So sk plus 1 into y of x is equal to integral from 0 to 1 t dt plus integral from 1 to s of minus t dt where epsilon to 1 to plus infinity closed interval. So sk plus 1 into y of x is equal to t square by 2 from 0 to 1 minus t square by 2 from 1 to x where epsilon to 1 to plus infinity closed interval. So sk plus 1 into y of x is equal to 1 by 2 minus sk by 2 minus 1 by 2 where epsilon to 1 to plus infinity closed interval. So sk plus 1 into y of x is equal to 1 by 2 minus sk by 2 plus 1 by 2 where epsilon to 1 to plus infinity closed interval. So sk plus 1 into y of x is equal to 1 minus sk by 2 where epsilon to 1 to plus infinity closed interval. So y of x is equal to 2 minus sk over 2 into sk plus 1 where epsilon to 1 to plus infinity closed interval. Thus from equations 1.12 and 1.13 we have y of x is equal to sk by 2 into sk plus 1 where epsilon to 0 to 1 close open interval and y x is equal to 2 minus s square over 2 into s square plus 1 where epsilon to 1 to plus 1 the closed interval, which is required solution of the initial value problem 1.9 and is defined over 0 to plus 1 the closed interval. Well, this is graph of the solution of the initial value problem. The solution is continuous from 0 to plus infinity closed interval. Also, solution is differentiable from 0 to infinity closed interval except at s is equal to 1. Well, see another exercise. Find solution of the initial value problem dy by dx plus px into y is equal to 4x, where x belongs to 0 to plus 1 closed interval, and y at 0 is equal to 3, where pux is equal to 4x belongs to 0 to 1 closed interval, and pux is equal to minus 2 by x, 4x belongs to 1 to plus 1 open interval. Also state the interval I is subset of R over which the solution is defined, and draw the graph of the continuous solution. Well, see solution. For epsilon to 0 to 1 closed interval from only 1.14 we have dy by dx plus 2y is equal to 4x, where epsilon to 0 to 1 closed interval. Comparing the ODE 1.15 with standard form we have px is equal to 4 epsilon to 0 to 1 closed interval. So integrating factor is mu x is equal to exponential of integral of px dx, which is equal to exponential of integral of 2 dx, which is equal to exponential 2x, where epsilon to 0 to 1 closed interval. Multiplying the OD 1 by 15 by the integrating factor exponential 2x, we have exponential 2x dy by dx plus 2 exponential 2x into y is equal to 4x exponential 2x, where exponential to 0 to 1 closed interval. Well, this can be expressed as dy by dx of exponential 2x into y is equal to 4x exponential 2x, where exponential to 0 to 1 closed interval. So d of exponential 2x into y is equal to 4x exponential 2x dx, where exponential to 0 to 1 closed interval. Now integrating we have integral of d of exponential 2x into y is equal to integral of 4x exponential 2x dx plus c1, where exponential to 0 to 1 closed interval and c1 is arbitrary constant. So exponential 2x into y is equal to integral of 4x exponential 2x dx plus c1, where exponential to 0 to 1 closed interval and c1 is arbitrary constant. So exponential 2x into y is equal to 4x into exponential 2x over 2 minus integral of 4 into exponential 2x over 2 dx plus c1, where exponential to 0 to 1 closed interval and c1 is arbitrary constant. So exponential 2x into y is equal to 2x exponential 2x minus exponential 2x plus c1, where exponential to 0 to 1 closed interval and c1 is arbitrary constant. While dividing this by exponential 2x, we have y of x is equal to 2x minus 1 plus c1 exponential minus 2x, where exponential to 0 to 1 closed interval and c1 is arbitrary constant. Now using the initial condition 1 by 14, that is y at 0 is equal to 3, we have 3 is equal to 2 into 0 minus 1 plus c1 exponential of minus 2 into 0. So c1 is equal to 4. Therefore, from equation 1 by 16, we have y of x is equal to 2x minus 1 plus 4 exponential minus 2x, where exponential to 0 to 1 closed interval, which is solution of the initial value problem 1.14 on 0 to 1 closed interval. Also for exponential to 1 to plus infinity open interval from equation 1.14, we have dy by dx minus 2 over x into y is equal to 4x, where exponential to 1 to plus infinity open interval. Comparing the OD 1.18 with standard form, we have px is equal to minus 2 over x, where exponential to 1 to plus 20 open interval. So integrating factor is mu x is equal to exponential of integral of minus 2 over x dx, which is equal to exponential of minus 2 log of x, which is equal to exponential log of x exponential minus 2. So mu x is equal to x exponential minus 2, where exponential to 1 to plus 20 open interval. Multiplying the OD 1.18 by the integrating factor 1 over x square, we have 1 over x square into dy by dx minus 2 over x cube into y is equal to 4 over x, where exponential to 1 to plus 20 open interval. So d by dx of y over x square is equal to 4 over x, where exponential to 1 to plus 20 open interval. So d of y over x square is equal to 4 over x dx, where exponential to 1 to plus 20 open interval. Now taking integral, we have integral of d of y over x square is equal to integral of 4x dx plus c2, where exponential to 1 to plus 20 open interval and c2 is arbitrary constant. So y over x square is equal to 4 into log of x plus c2, where exponential to 1 to plus 20 open interval and c2 is arbitrary constant. So y over x is equal to 4 into log of x plus c2 into x square, where exponential to 1 to plus 20 open interval and c2 is arbitrary constant, which is solution of the OD 1 by 14 on 1 to plus 20 open interval. Now since the solution of the initial value problem 1 by 14 is continuous from 0 to plus 20 closed interval, and in particular at s is equal to 1, therefore from equations 1.17 and 1.19 we have 2 into 1 minus 1 plus 4 into exponential of minus 2 into 1 is equal to 4 into log of 1 plus c2 into 1 square. So c2 is equal to 4 exponential minus 2 plus 1 Therefore, y(x equal to 4 into log of s plus 4 exponential of minus 2 plus 1 into s square, where exponent to 1 to plus 20 open double. Thus, from equations 1.17 and 1.20, we have y(x is equal to 4 into exponential of minus 2s plus 2s minus 1, where exponent to 0 to 1 close interval, and y(x is equal to 4 into log of s plus 4 exponential of minus 2 plus 1 into s square, where exponent to 1 to plus 20 open interval, which requires solution of the initial value problem 1.14 and is defined and continuous over 0 to plus 20 close interval. Well, this is graph of the solution of the initial value problem. The solution is continuous from 0 to plus 20 close interval. Also, solution is differentiable on 0 to plus 20 close interval except at x is equal to 1. That's it for today. See you in the next lecture. Don't forget to share, like, and subscribe. Easy Math with Dr. Nasir so you never miss a conceptual concrete lesson.